Hi, this is Earth Science teacher Tim Martin, and in this astronomy video I want to discuss the leftovers of supernova, neutron stars and black holes. If you haven't had the opportunity, I'd encourage you to go back and watch the videos I produced about the evolution of a typical star, as well as the video about supernova. But let's take a look at these leftovers from supernova. As we talk about the evolution of a supermassive star, it's important to remember they start out as a nebula, then go on to a protostar, a blue giant star, a red supergiant, and then on into the violent supernova explosion. At this point, the path may diverge. If a star has between 1.3 and 2 times the mass of the Sun down in the core, the leftover may become a neutron star. On the other hand, if we have greater than 2 solar mass in the core, our likely leftover will be a black hole. Let's take a look at both. For a star that has between 1.3 and 2 times the mass of the Sun in the core, when the core of the star collapses in the violent supernova explosion, electrons will get smashed into protons, forming neutrons. In fact, the whole star becomes a big ball of neutrons. The star core becomes as dense as the nucleus of an atom. At this point, it's good to remember that the nucleus of an atom is 10,000 times smaller than the entire atom. So, if we compress the electrons down into the protons forming neutrons, since the neutrons have no electrical charge, they pack very closely together. The core of the star becomes incredibly dense. In fact, the density is something like 100 million tons per cubic centimeter. That's like taking all of the cars in the United States and smashing them down into the size of a playing die. The entire star, which remember was quite large, now is crushed down to having a diameter between 30 and 40 kilometers. For those of us here in central North Carolina, that means the core of a neutron star would nicely fit between the cities of Greensboro, High Point, and Winston-Salem, as we can see in this map of North Carolina. For those of you not familiar with central North Carolina, maybe you're familiar with New York City. If we dropped a neutron star on New York City, well, it would nicely fill New York Harbor. Neutron stars have strong magnetic fields, and associated with those magnetic fields, often material is ejected out in bright jets. To understand this, it's helpful to think about a lighthouse. As the light rotates, we can see that beam sweeping across the surrounding space. Something similar goes on in the supernova explosion. In this violent crush, the star core collapses and it starts rotating extremely rapidly. The strong magnetic field may eject particles out along in a beam along the poles of the magnetic field. Now, when I say rotating rapidly, some neutron stars are known as millisecond pulsars. This pulsing results from the star spinning at more than 1,000 times per second. Here we can see a time lapse of the Crab Nebula supernova remnant. The images in blue in the center were taken by the Chandra X-ray Observatory. Here we can see material being ejected away from the neutron star as it wildly spins in the center of the Crab Nebula supernova remnant. But really, really big stars do even more dramatic things when they die. They'll start out as a large nebula, then form an enormous protostar. The protostar may form a blue supergiant. The blue supergiant will evolve into a red supergiant, and the red supergiant can go into a very violent supernova explosion, and that may go on to become a black hole. So what is this thing that we call the black hole? If a star has more than twice the mass of the Sun in the core, it will become a violent supernova, sometimes referred to as a hypernova. During the violent core collapse, matter is actually pushed to occupy the same place in space. What I'm saying is the volume of the entire star becomes a point. This is where the math gets a little bit interesting. If the volume becomes zero, well, what does that do for density if density is mass divided by volume? Well, technically we can't do that math. However, as the volume approaches zero, we can see that the density skyrockets. So we can say that the density approaches infinity. In this case, gravity of this object becomes so great that not even light can escape. Black holes are often depicted as sort of a funnel shape like this. Why is that? Well, if you can imagine a rubber sheet that's stretched tightly with a mass in the center, it will warp downwards. Just like that two-dimensional sheet is warped by the heavy mass, a black hole can warp three-dimensional space. So, do these things really exist in space? The first candidate for a black hole was discovered in the 1960s, Cygnus X1. We knew this area of space produced strong X-rays. What we know now is this star, 6,000 light years from home, is a blue giant star that is orbiting very close to something. Very close, as in 0.2 astronomical units. That's approximately half the distance between Mercury and the Sun. The object that this blue star is going around? Well, it's too small to see. The blue star appears to be going around nothing. But when we calculate the mass, the nothing that star appears to be going around is 14.8 times heavier than the Sun, making it an excellent candidate to be a black hole. We know there's a disk of material around the black hole. Just before material falls into the black hole, it can emit a blast of X-rays. We can see these accretion disks, or disks of debris, around black holes in several places in space, such as we see in this Hubble telescope image of NGC 4261, a galaxy that's 100 million light years away. By measuring the disk's properties in the center of this galaxy, we know that this material is orbiting a black hole that's 400 million times the mass of the Sun. Similar to neutron stars, it's also common that black holes may have jets. In this case, jets are streaking outwards 88,000 light years from the central core of this galaxy. Early in 2019, news was made by the Event Horizon Telescope. We knew there was a black hole in the center of the giant elliptical galaxy M87, located 53 million light years away. By studying the central region of this galaxy with Hubble Space Telescope, we were able to see jets streaming away from the center of this galaxy. Using a network of radio telescopes around the world, the Event Horizon Telescope was able to capture this first direct image of a black hole in the center of a distant galaxy. This particular black hole is 5 billion times the mass of the Sun. Black holes truly are incredible objects, but there are a lot of misconceptions about black holes. I'd like to review a few details about what black holes are and also what they are not. So for starters, black holes are objects with an escape velocity greater than the speed of light. Now let's just imagine that I could go in a black hole. It's not a good plan to think about going near or into a black hole. But if we suspend that for a moment, inside of a black hole, if I took a powerful laser and turned it on, the light would not be able to escape. Even traveling at 300,000 kilometers a second, not even light could escape a black hole. Another property of black holes, they're objects with a radius less than or equal to the Schwarzschild radius. Well, that's a little bit of a mouthful, but the Schwarzschild radius, also known as the event horizon, we talk about large black holes or small black holes. If black holes truly are a point, where does the size of a radius come from? Well, this is the point of no return. Again, it's not going to be possible, but imagine if we could find a way to stand right at the event horizon or the Schwarzschild radius of a black hole. Within the event horizon, nothing could be escaping. Right at that point, the orbital velocity of the black hole would be equal to the speed of light. We could imagine that if you were standing right at the event horizon or right at the Schwarzschild radius and turn on the laser beam would actually go into orbit around the black hole, entering the back side of the laser. Another fun thing we can think about is that by looking forward, you would be able to see the back of your very own head. Another property of black holes is their volume. Once material or an object crosses the event horizon, it will go down to the singularity and have a volume of 0. This, of course, means that its density approaches infinity. Well, besides these 4 properties of what black holes are, let's talk about what black holes are not. With all apologies to Star Trek and other space movies, black holes are not a place to do time travel. The mathematics that help us understand black holes also lead us to the understanding that there may be black holes that have multiple openings. We know of these as wormholes. Unfortunately, the mathematics that predict these exist also predict that when material enters a wormhole, it will go into the singularity and be stuck there for good. So I highly don't recommend boarding a shuttlecraft or any other spaceship to travel through a wormhole or a black hole. Lastly, black holes are not giant vacuums that suck up everything around. This is a common misconception. Don't worry, it won't happen, but if the moon turned into a black hole right now, we would simply have a black hole that orbited the Earth every 27.3 days. If the sun turned into a black hole, again, don't worry, it won't. Our star is too small to become a black hole. But if the sun turned into a black hole, we on planet Earth would simply orbit that black hole every 365.25 days. Black holes have immense gravity, and they're not giant vacuum cleaners that suck up anything. The properties of gravity are simply based on the mass. So if I became a black hole and you don't feel my gravitational attraction, you would never know that I existed. Speaking of this property, that they're not vacuums, but they do have immense gravity, it's worth noting one final thing about the gravity of a black hole. This image on the left, taken by the Chandra X-ray Observatory, is showing us the center of the Milky Way galaxy where there is a large black hole. These images on the right, however, are data from the European Southern Observatory, where we can see the stars orbiting around the black hole in the center of our galaxy. Because of this immense gravitational attraction, some of these stars are moving incredibly fast. As it turns out, the black hole in the center of the Milky Way is 4 million times heavier than our star. There's a lot more to explore about black holes, neutron stars, and other amazing things in space. I hope you can join me again on another Team Art Science video.